Hi everyone, in this video we are going to discuss natural gas. So you might have heard natural gas be referred to as methane, but that's not entirely correct, so let's just try to refer to it as natural gas or as a fossil fuel. I'd prefer this one. So natural gas is a fossil fuel in the gaseous state, right? So now natural gas is primarily comprised of one hydrocarbon, which is called methane, but there are a number of other trace impurities that also exist in there. So just calling it methane is not actually correct. So we will say natural gas from here on out. Now, inside natural gas, we have methane primarily, but we also have some carbon dioxide, and there's a lot of water vapor, more than you would think. But the cool thing about methane, right, which methane has the formula CH4, is that it is extraordinarily explosive. So it just takes a tiny little spark and then boosh, you have this huge explosion. It is so cool. YouTube it if you want to see a video of it. It's really neat. Now, that's not that important. The second thing that's actually just kind of a fun fact is that methane is odorless. So when you use natural gas in your home, we actually sneak a little chemical into it as well, so that if there's ever a leak and your house is filling up with gas, you're not just sitting there smelling in the methane and acting like nothing's wrong. You can actually detect this other chemical, you can smell it and say, oh my gosh, I have to get out of here. So that's just kind of a fun fact. So let's look at the history of using a number of different energy sources here on this planet. So before the 1800s, and this is a review, before the 1800s, we primarily used wood as our main source of energy. From the years 1800 to about 1950, we switched to coal. Okay. After that, from 1950 to now, we primarily use petroleum. But what's really interesting is in the year 1980, we actually started using natural gas. And so all three of these right here are just different versions of fossil fuels that we have started to use, but essentially set on fire. And so we've done a combustion reaction with all of these to grab the energy or the heat that's evolved from those combustion reactions. So let's talk about some numbers when it has to deal with natural gas. So let's look at the 1980s and the year 2015. And let's look at this for U.S. and global consumption. And before I do this, I need to introduce one unit, and that is called TCF, which is trillion cubic feet. And so that's how we measure our methane consumption. It's kind of a weird unit, but trillion cubic feet is essentially it. So back in the 1980s, we as Americans were using about 22 trillion cubic feet per year. And then up in 2015, so this current year, we're using about 30. It's just under 30. It's a little over 29 right now, trillion cubic feet per year. Now, globally, back in the 1980s, they were only using around 50 trillion cubic feet. So the entire planet was using about 50 trillion cubic feet per year. Now, in 2015, we're actually up to a number of about 110 trillion cubic feet. So just in about 30 years, we have more than doubled our number of natural gas consumption. That's a lot. I mean, that's a lot to think about. But the problem is natural gas is a gas. And so there's all of these inherent problems that show up when you're trying to use gas as a source of energy. So think of storage, think of transportation. There's a lot of things that are more difficult when you're using something sneaky like a gas, because it could very easily get out of its container. So keep that in mind. All right, so before we go any deeper in this, I want to review methane, because methane is primarily what natural gas is comprised of. And I want to ask you two questions. The first one, what is the molecular geometry of methane? Go. All right, did you get an answer? Hopefully you did. And so what you needed to do was remember that methane has the molecular formula of CH4. So we put carbon in the center, connect it to 4 different hydrogens, and what we see is that methane has a tetrahedral geometry. Yes, you should have known this by this point. You absolutely need to know geometry. So methane is definitely tetrahedral. Now, let's see what else we remember. What are the bond angles? Go. All right, did you get an answer? Hopefully you did. Essentially what we were trying to do was determine the angle between the hydrogen, carbon, and other hydrogen, and that bond angle, whenever you have a tetrahedral molecule, especially with no lone pairs on that central atom, we would have a bond angle of 109.5 degrees Celsius. Does it matter if you put 0.5? Yes, you absolutely have to say 109.5. We can be that specific, so I expect you to be that specific. All right, so now, how do we do this? How do we capture the gas? How do we change it? Like, what do we do with this? Step one, the first thing you do is you drill down deep okay, into these wells where we have our natural gases stored. So you drill. Typically, they're in wells that are very, very close to other sources of oil or coal, so they're commonly found around these other fossil fuels. Number 2, and this is super important, we scrub it. So we scrub the methane to remove a number of different impurities, but there's 4 that I want you to be very much aware of. So we definitely are removing water vapor, so that's in the gaseous state. We are definitely removing as much carbon dioxide as possible. We also want to remove our hydrogen sulfide, so that's a real nasty gas. I have some friends that work with it, and their eyes get very, very swollen and red, and they look it's really bad. So it's a nasty gas you want to avoid, so it's a really good thing that we scrub it and remove it from our source of fuel, essentially. And the last one is helium. Helium is just an inert gas, so there's really no point of trying to blow it up, and it's just wasting our energy. So we're just trying to purify our natural gas to be as efficient as possible. All right, so now then what we do is we put it into something that kind of reminds me of a coal plant. It's not the same, but the structure is a little bit similar, so hopefully you can use that to picture this. So you start off with, after you've drilled and scrubbed this, you have to do that first, then you start off with your source of methane. So it's a gas, so we'll just put it in a cylinder. So what we do is we pump that to a boiler. Okay, this part's almost always the same for the 3 things. So there's a boiler. For a boiler, you have to add heat. We know this. And so essentially what we're doing is we're taking that methane and giving it as much heat energy, as much thermal energy as possible. So all of those molecules, all those methane molecules are now vibrating around like crazy. They've taken in as much kinetic energy as possible. So they have a lot of kinetic energy. And then what we do is we send it on to a turbine. So we know this part. We send it onto a turbine, and so I draw mine like this, kind of funky looking, but essentially remember a turbine spins. So you've got this methane, it's going through the boiler, it's all of a sudden it has all this kinetic energy, it goes through and it hits your turbine starts to spin. Spin, 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 spin. Your turbine, remember, is connected to a generator, and so there's this like tube on the other end of the turbine that has wire coils, and it essentially, that part starts to spin. So the turbine spin, which forces your wire coils to spin, this is now spinning inside of your generator. And if you recall, your generator is surrounded in a magnetic field. And so as this coil spins, you essentially change your mechanical energy to electrical energy. So let's go through this. Right here in our methane by itself, just sitting by itself, we have a lot of potential energy. Then we heat it up so we give as much kinetic energy as possible. Goes to the turbine, we convert our kinetic energy to mechanical energy. Then it hits our generator, and then we convert our mechanical energy to electrical energy. And then this is what goes out into our public, and we get to use our energy in terms of electricity. So it's awesome. So very, very simple system, and obviously I've simplified this a lot, but essentially that's how this system works. So why do we do this? Well, it has to do with the amount of energy that is evolved when we put methane through a combustion reaction. Essentially, we get about 50 kilojoules of energy evolved, of heat energy evolved per gram of methane. That's a lot. That's a lot. That's a huge, huge number. And so you should be super happy to see that, because natural gas may be where our energy system is moving in the future, okay? Last question to make sure we understand this. Which fossil fuel releases the most energy upon combustion? Okay, so you have to use your brain to figure out what our 3 fossil fuels are that we talk about in this course, and then let's just say we're just burning 1 gram of each one. Which fossil fuel? Go. All right, did you get an answer? Hopefully you did, but just in case you didn't, let's review. Our 3 fossil fuels, we have natural gas, that's your fossil fuel in the gaseous state. We have petroleum, that's your fossil fuel in the liquid state. And then we have coal, that's your fossil fuel in the solid state. So now coal, best version of coal, if we're using our anthracite, gives us about 30.5 kilojoules of heat evolved per every gram burned. Petroleum is closer to 48 kilojoules per gram burned, and then natural gas brings in at about 50 kilojoules per gram. So natural gas is the clear winner here. And that's it for today. Have a great week. Take care of yourself and drink water.